Now we're getting to new stuff. Chapter least squares problems. Okay. So here's a problem we're going to consider, at least for the first portion of this chapter. So still A equals B, but A is m by n, so it's not necessarily square anymore. M is assumed to be greater than or equal to n. So we may have more equations and unknowns in the overdetermined system. And we'll also assume is the word full rank part comes in. The rank of A is equal to n. So that's since that's also the number of columns, we say that A has full column rank. The way of putting it is that the columns are soon to be linearly independent. So for the first couple sections, we're going to go with these assumptions. So in 4.3, I'll talk about what's called the rank deficient least squares problem, where the columns are linearly dependent. Okay. Okay. Also, from the consequence of having linearly independent columns is A is non-singular. Now, I have to be careful about my terminology here. Normally, I use non-singular as being synonymous with invertible, but that's only true for square matrices. If the matrix is not square, we can't even talk about an inverse. Although there is a pseudo inverse, which we'll see later. But the notion of being singular and non-singular applies whether A is square or not. Because really the definition of being non-singular has nothing to do with invertibility. It's about this. AX is equal to 0 if and only if X itself is 0, which really is another way of phrasing the notion of linear independence of the columns of A, because A times X is a linear combination of A's columns. The definition of linear independence says that if some linear combination of vectors is a 0 vector, and the only way that could happen is if the coefficients in the linear combination are the 0 vector, that's linear independence. So, okay. All right. So under these circumstances, certainly when m is strictly greater than n, it's possible that X equals B doesn't have a solution at all. This system has a solution if and only if B is in the range of A. So if you consider the set of all possible linear combinations of the columns of A, that's not going to span the entire space Rm if n is greater than n, because you only have n columns. But if B happens to fall within that set of linear combinations, then such a linear combination is the solution. So we don't necessarily have existence. But because of linear independence, if a solution does exist, it is unique. That's what the full column rank list of A gives us. Actually, all right, I'll just give an example. So suppose A is a 3x2 matrix. 0, 1, 0, 0, 0. It's a very simple one. And then if I let B be equal to 1, 1, 1. Well, that is not in the range. Okay, so AX equals B has no solution. Because we can see that any linear combination we can conceive of the columns of this matrix would have the third component of the resulting vector be 0, no matter what. So if your right-hand side B has a non-zero third component, there's not going to be any solution. But if it is 0, a solution will exist. So in cases where there is no solution, what can we do? Also, even if there is a solution, we may not know. Like, how would we get it? Actually, I'm trying to think about it. Suppose if AX equals B, well, okay. If AX equals B does have a solution due to B being in a range of A, and let's say A is a rectangular matrix, you could do Gauss elimination. What would happen is you would have M minus N rows turn out to be entirely 0. You would have experienced this in your first linear algebra class. And because of B being in a range of A, the corresponding elements of B would also be made 0 by the Gaussian elimination row operations. Then you end up with a square n by n system to solve. But we're interested in the case where B is not in a range of A. If we can't solve a problem, what can we even do? The idea is to come as close as possible to a solution. So we guys need to find X such that the norm of B minus AX is minimized. So we may not be able to make B minus AX 0 because there's no solution. But if we can make it as small as possible, having an approximate solution can be valued in whatever application you have. Right. Now, I haven't said which norm, and last time we talked about different kinds of norms, 1 norm, 2 norm, infinity norm, etc. So what's a good norm to use? Because if I try to solve this problem using different norms, like whatever X minimizes this quantity in the 1 norm sense will be generally be different than what would do it in the 2 norm sense. Okay, so what we're going to go with is the 2 norm, also known as the L2 norm. And the reason for that is, as I mentioned last time, the 2 norm is a differentiable function of the elements of the vector you're taking the norm of. That way, to find a minimum of a 2 norm, we can use minimization techniques from calculus. Okay. Now, because the 2 norm of a vector, the square root of the sum of squares of the components, we're trying to minimize a sum of squares. So this leads to a problem that we're looking at being called the least squares problem. I remember when I was a freshman, I was taking a physics class, the first day in a physics lab. We're given all these guidelines and so forth about preparing our lab reports. And I guess for doing plots and so forth. He said, oh, you're going to use least squares. And I never heard of that. Like, am I supposed to know about this? What is this? I guess it wasn't until a statistics class, actually a few years later, like my senior year in college, that I found what the hell least squares was. Never imagined I'd be teaching about it, but we'll figure. Yeah, come a long way. So, oh, where's the eraser? So now we're going to try using the approach of multivariable calculus to find the minimum of what x minimizes a 2 norm of b minus ax. So two norm. Now, since that is a square root of sum of squares, we're actually going to look at the 2 norm squared, because minimizing that certainly minimize its own square root. And the reason for that is the 2 norm of a vector squared is the same as the inner product of a vector with itself, or dot products. Okay, this is an inner product, but okay, because remember, if two vectors u and v, u transpose v is the dot product, or inner product of u and v. Now, I need to find a function phi x to be equal to this dot product. So to find a minimum, so dust off your multivariable calculus knowledge. Well, actually, did anyone tell me if I have some function phi and I want a function of several variables, and I want to find where it has a minimum, what do I need to find out?
Partial. Partial sentence is 0.
Yeah, so all the first partial derivatives of phi to be 0. Another way of writing it is that the gradient of phi be equal to the 0 vector. So it's equivalently partial phi with respect to xi is equal to 0. All right, so that's one thing. So that gives us a critical point that could be a maximum or minimum, or even worse, a saddle point, or maybe nothing at all. What's the second condition for ensuring that the critical point we find is actually a minimum and not something else?
Take the partial and the partial.
Yeah, so it gets some second derivatives. So the matrix of, take all the second partial derivatives of phi, that would be a matrix. And since this is going to be a continuous function, it'll actually be a symmetric matrix. So, and so it's on single variable calculus. For a minimum, you want the first derivative to be 0 and the second derivative to be positive. The multivariable analog of that, that the Hessian, which I'm going to denote by h phi, Hessian, if it's already going to be symmetric, it's also positive definite. I find it amusing in multivariable calculus text that deal with like a minimum over, let's say, a function of two variables, they say conditions on the second derivatives that are equivalent to the Hessian being positive definite, but they're not going to say that because it's a calculus text, not a linear algebra text. But and actually, I feel like if linear algebra was introduced sooner, then generalizations from single variable to multivariable could be described so much more cleanly. But they don't do that, and I have to tiptoe around a linear algebra in classes like that, which is kind of aggravating. And if I mention linear algebra, the students get mad at me. It's like, we're not expected to know that. It's like, I'm just mentioning it for the interest of people who are, who do know it. So, but yeah. Okay, so, and for precise definition, the IJ entry of the matrix H5 is the second partial derivative by respect to xi and xj. And the Hessian is symmetric. Okay. Okay. Now, before we get into defining the minimizer of our particular function, b minus ax, I'm going to give some multivariable differentiation rules. Okay. That we'll end up using for this, but they're very good to know in general. Okay. So we have a multivariable function that is just C transpose X, where C is a constant vector. So this is a function that is linear function of a component of X. So that would be the same as the sum EJ XJ. So that would mean that the partial derivative of F with respect to Xi, well, you can think of keep in mind that the partial derivative of Xj with respect to Xi is equal to 0 if I is not equal to J, and 1 if they are equal, because all these X's, they're independent variables. So if I take the derivative of this with respect to Xi, all the terms are going to be 0 except for one of them, where J equals I. So then I take the derivative of that, and I'm just going to get, so I get Ci. So in other words, the gradient of F is equal to C. I guess depending on how your conventions and so forth, you might call the gradient a row vector, but we're not going to need to get into that. Which makes sense because if you have a function, 2x, the derivative is 2. So it's just a multivariable analog of that. Now, that's a linear function. We're also going to need a quadratic function. That's going to be more interesting. Let's find the function g of x to be x transpose bx for some matrix B. Okay. Now, the formula for this in terms of entries of x and b is a sum. Now, B has to be a square matrix for this. I goes 1 to n, j goes 1 to n of Bij xi xj. This is called a quadratic form. It's all the terms here are of degree 2 in terms of the components of x. All right. So now I'm going to take the derivative of this with respect to one of these x's. I'm already using the indices I and j, so I'll just use k. So partial derivative of g with respect to xk. So from the linearity of the derivative, I have a product rule thing going on here. Like I have xi times xj. So, okay, so I'll have a sum times 1 to n, j equals 1 to n, bij. And now for taking derivative of this product, I use a product rule. So I'm going to get, okay, Kronecker delta ik xj plus xi Kronecker delta kj. Now remember, Kronecker delta is actually, this is right here. Kronecker delta has two indices, and it's equal to 1 if the indices are equal, like for instance, diagonal entry in an identity matrix, or equal to 0 if the indices are not equal. So for a product rule, I'll have xj times the derivative of xi. But the derivative of xi with respect to xk is 0 unless I is equal to k. That's the first type of product rule, and then similar over here. Now, since most of these are 0, we can strip this down quite a bit. It'll be easier to break it up into two sums. So if I look at this first part, this is going to be 0 unless I is equal to k. So actually, so the outer sum I can get rid of. I'll have sum over j be kj xj. So this part reduces to that. And then over here, this is going to be 0 unless j is equal to k. So I'll have the sum over I still there. And then wherever I have j, I put k. So I'm going to have b I k x I. This is the formula for matrix vector multiplication. This is the kth component of b times x over here. Now, because when you have a matrix vector product, the second index of a matrix element, the column index, matches the index of a vector you're multiplying with. The row index for a matrix element, that indicates which component of a matrix vector product you're computing. Here we don't have that. Here we have xi, but I is the row index, not the column index. So this is not a matrix vector product involving B, at least. But how can I describe this as also the kth element of a matrix vector product? How do I deal with the fact that these indices are like in the wrong order? Take a transpose.
Transpose it?
Yes. So it's, so you have B transpose X in that case. So in summary, the gradient of G is equal to B plus B transpose times X. So if you use symmetric, you'd have 2bx. Now, this is a generalization of the rule for taking a derivative of x squared. Take a derivative of x squared, you get 2x. So this generalizes that. Okay. So, questions so far? All right, so now I have all the gradient rules that I need. Okay. Now, what about the Hessian? Well, the Hessian of f would be 0. And if you take a linear function, second partial derivative is a linear function of 0, so we don't need the Hessian of f. Remember, the gradient is a vector. The Hessian is a matrix. So if I were to take the, now we have a linear function of x. So the gradient is a linear function. The Hessian, therefore, is going to be a constant. So I won't go over the whole differentiation process, but so for Hessian, based on these examples, Hessian of F, 0 matrix, Hessian of G is just a matrix from the gradient, B plus B transpose. And no matter what B is, B plus B transpose is a symmetric matrix. As I mentioned earlier, the Hessian generally is symmetric. So we get that. All right, so so now I have the differentiation rules I need. I'll bring back my a function I'm interested in. B minus AX transpose B minus AX. So before I can apply my differentiation rules, I need to expand this dot product. So that's going to be B transpose B minus X transpose A transpose B minus B transpose AX plus X transpose A transpose AX. Right. Now we assume that everything is real. These terms are actually equal because both of them can be written as both of these can be written as using properties of transpose. A transpose B transpose X. Because each one of these is a number, so it's equal to its own transpose. And using a property that the transpose of a product of transposes in reverse order, you can show that both of these are equal to this. All right. So now we write this as B transpose B minus 2 B transpose B transpose X plus X transpose. I'll put the A transpose A in parentheses. X. Now ready to do gradient. Gradient of phi. Well, B is a constant vector, so this part will have a gradient of 0. Here, this is like the function f. It's some vector transpose x. So the gradient is just going to be that vector. So get minus 2 A transpose B. And then here, you have X transpose times the matrix times X. So this was playing a role of B earlier. So the gradient of that would be this matrix plus its transpose all times X. But this matrix is symmetric. If you were to take the transpose, that's using that same property. Product of transpose of a product, the product of transposes in reverse order. A transpose A transpose is itself. So what we're really going to get is 2 times this matrix times X. I just noticed in the notes, I defined phi to be not this, but 1/2 times this to get rid of these pesky factors of 2, but oh well. All right, so that's the gradient. And we want this to be equal to 0. And then the Hessian of phi, this won't contribute anything because this is a constant now. So the Hessian will actually come from this matrix. So it's going to be 2 A transpose A, which is positive definite. So whatever critical point we find is in fact going to be a minimum of phi, which is what we want. So the gradient of phi is equal to 0 if and only if this system equation is satisfied. A transpose A X equal to A transpose B. Setting that equal to 0. And so this is what we solved to solve the least squares problem. These are called the normal equations. Okay. Oh, you know what? I actually haven't shown that A transpose A is positive definite. I've shown it symmetric. It is positive definite though. And I'll explain why. If we let X be non-zero, then, okay, so I'm premature in saying that. All right, if we assume that X is non-zero, that means that AX is also non-zero due to A having whole column rank or being non-singular. So that means that the norm, or any norm, of AX is strictly positive. But if I write out the 2 norm squared, that means that's X transpose times A transpose A times X is now known to be positive. That is what tells us that A transpose A is not only symmetric, but also positive definite. So that's where we need to show. And because it is positive definite, it must be non-singular. And A transpose A is square, so when I say non-singular, it also means it's invertible. So the normal equations are guaranteed to have a unique solution in this full column rank case. Okay. So it might seem like, as far as these squares problems are concerned, we're done. Like, why are we even here now? Because most of those memes have been out there lately. I think largely about Star Wars, where things go, they have things going a little differently, and therefore the whole thing is over. And then they cut to written and directed by George Lucas. So yeah, it seems like we're done. Now, okay, there's only about the full rank case. We will talk about rank deficient cases sometime later. Actually, I think a couple weeks from now. So we're actually going to spend a lot of time on this. But the reason why we're not really done, even though we do have a way to solve the problem, is the matrix A transpose A can be ill-conditioned. In fact, the condition number in the 2 norm of A transpose A, which is defined to be the norm of A transpose A times these are all 2 norms, times the 2 norms of A transpose A inverse. It can be shown and okay, in the book for assigned as homework problems, I do not recall if I actually assigned these homework problems, but they're homework problems. Homework problems for somebody, is actually the condition number of A squared. So in other words, if A itself is already ill-conditioned, we just made it a whole lot worse by going for normal equations. Now, if we are going to solve the normal equations, and sometimes it's actually not a bad idea. This is back to like chapter 3 stuff, because we have a square matrix that's invertible. So we have various methods from chapter 3 that could be used to solve it. But what would be a preferable way to solve this system of equations based on what we saw from the last chapter?
Isn't A transpose A is symmetric as well?
Yes, symmetric and positive definite.
Deconstruction, the LU decomp.
Well, the nice thing about LU is that you don't have to pivot. But there's a reason why it's not the best way to go for a symmetric positive definite case.
Because you can well, I mean, it's a symmetric thingy. The Cholesky.
Yes.
When you think symmetric positive definite.
Yeah. Yeah, so because it takes half the number of floating point operations. LDLT is also a good idea. Sometimes I think that's better because you don't have to take square roots, but people still like Cholesky, so. Well, actually, well, I think it's possible that LDLT might be somewhat more flops because you have a diagonal system also. But yeah, Cholesky is generally where it's at. So yeah, so you get Cholesky factor of A transpose A, and so then you're solved using forward and back substitution. Okay. All right, so because of this ill conditioning, people are not keen on solving a system involving A transpose A, if A itself is ill conditioned. So we're gonna see if we're gonna look into another way of solving the least squares problem. Um, So here we're going to use orthogonal matrices. We're going to recall that matrix Q, which is we're assuming is okay. Oh, actually, well, it's got to be square. We're going to assume it's M by M is orthogonal if Q transpose Q is identity. Now we're putting it, the inverse of Q is actually the transpose of Q. That's quite convenient. So a property of Q that will be of use to us is the following. If I take a vector X and multiply it by Q, and then I take the 2 norm, I'll focus on the 2 norm squared for convenience. So that would be QX whole thing transpose QX. That would be the same as X transpose, Q transpose Q, X. But Q transpose Q is identity. Now we're left with X transpose X, which is the 2 norm of X squared. So multiplying a vector by an orthogonal matrix does not change its norm or its 2 norm or its Euclidean length. So the main idea behind this alternative approach is use the fact that the 2 norm of B minus AX that we're trying to minimize is equal to 2 norm of some orthogonal matrix transpose times B minus AX. Q is orthogonal. Okay. So use a factorization which I've not mentioned before, and I'm actually going to spend the next 2 or 3 class periods talking about. So we covered it pretty exhaustively. So the QR factorization A, which is M by N, so spatial whatever size, equal to Q times R. So Q is M by M. R is M by N, so same size as A. Okay. Now, Q is orthogonal, and R is upper triangular. Now, to work with a square upper triangular matrix, I could break Q down into two blocks. So these are groups of columns of Q. So here we have n columns, the first n columns of Q. And then here we have m minus n. Okay. And then I can break R down. So the top part would be R1, which is a square n by n matrix. And then because, and this is going to be upper triangular. And because upper triangular, the bottom part of R is going to be 0. So R1 is also upper triangular, but it's square. Okay. Because A is non-singular, that means that R1 is also going to be non-singular. And since R1 is square, that means it's also invertible. Okay, so I haven't said anything, and I won't be saying anything today about how we get the QR factorization. That's going to be subject of the next few classes. For now, we're just going to assume we can get it. So you go to MATLAB and do type QRA, and you have your QR factorization. What do we do with it to solve a least squares problem? Okay. So because if A is equal to Q times R, that means we can multiply both sides by Q transpose on the left. So Q transpose A is equal to R. So that means that the norm we're trying to minimize, B minus AX, is equal to 2 norm of Q transpose B minus Rx. Now, if I replace Q with this column decomposition, it's not going to have Q1 transpose, Q2 transpose times B, and then I'll replace R with its block structure. Okay. Okay. Oh, actually, I'll go one step further. So now we have a vector where the top part of it is Q1 transpose B. Bottom part of it is Q2 transpose B. And then here we have R1X. And then the bottom part of it will be the 0 vector. Now, when you take the 2 norm of a vector that's broken down into 2 portions like this, really what you're doing is you're taking this sum of squares of these components plus sum of squares of these components. So you add all of them up. And then take the square root of that. So if I look at the 2 norms squared, that's going to be equal to the 2 norm of the top part squared. That's going to be Q1 transpose B minus R1X, 2 norm squared, plus the bottom part, which is just Q transpose B, 2 norm squared. This part doesn't even depend on X. That just is what it is. So unless B happens to be in the range of A, we're going to have this non-zero part that we can't do anything about. What about this? Here we can, the idea is to find X so that this is as small as possible, but R1 is a square invertible matrix, and this is just some vector. So we now have a way to get X. So we solve this equation. Q1 transpose B minus R1X equal to 0. Or if I just write it this way, R1X equal to Q1 transpose B. And R1 being upper triangular, all we got to do is use back substitution. But once you have a QR factorization, the rest of this is quite easy. Now, getting the QR factorization is a lot of work, as you'll see. Okay. So to summarize our two approaches, to minimize the norm of B minus AX, the 2 norm of it. In other words, the norm of the residual. So when you're solving AX equals B, B minus AX is referred to as the residual. You can proceed in one of two ways. You can solve normal equations. A transpose AX is equal to A transpose B. Or you compute the QR factorization, A equal to QR. Then you solve R1X is equal to Q1 transpose B, where Q1 consists of the first n columns of Q, and then R1 is the upper n by n block of R. So everyone, and the solution you get will be the same, except for rounding error. So we're mathematically equivalent, but at least with this approach, you're not dealing with a squared condition number. So that's why QR is often preferable.
I don't recall if I have particular commentary about conditioning in the QR case. It's something I've read about, like in Golub and Van Loan. I just can't remember if I also included that. In mine, okay. Oh. Strangely, I didn't. Or at least he's not in this section, maybe it's somewhere else. Okay. Sorry, just quickly scrolling through that now. Okay, because we're actually gonna see 3 distinct approaches to computing the QR factorization that have various advantages. Okay. All right. Is that all I have for today? I think it might be. Yeah, okay. So that's what I'll start on next week is different approaches to computing QR factorization. And the QR factorization, even just within this class, is useful not just for least squares problem, like later on, we'll deal with computing eigenvalues. The QR factorization will be useful there too. Okay. Does anyone have any homework questions? Including from the online peanut gallery. Oh, all right. Well, okay, then I guess that's it. Or,
I was looking at some for this chapter.
oh, okay, yeah. All right, guess we're calling it good. Okay. I'll stop recording.